Let's look at special relativity, and this time we will look at a relativistic momentum and energy. So we've seen that time and length are affected when objects travel at relativistic speeds, and just as a quick reminder, we have time dilation given by this expression. So delta t is the dilated time, delta t naught is the proper time. V is the speed of the object, and it's a relativistic speed, so that means very, very fast. And c is the speed of light. And then in the length contraction equation, we have length contraction is the proper length, and again, v is the speed of the object, and c is the speed of light. Now, since time and length are affected by these relativistic speeds, we have to think that other concepts that we've dealt with in classical mechanics are going to be affected. So one of such concepts is classical momentum. And remember that momentum was mass times velocity, and it was a vector. And one important thing about momentum was that it was conserved. So now we can look at the relativistic momentum, and relativistic momentum is again P equals mv, but there is this additional term that has to do with the relativistic speed of the object, the particle. Another quantity that is affected by relativity is the energy, and this is the equation for total energy. So E is mc squared divided by square root of 1 minus v squared over c squared. And let's see what happens if we set v equals 0. So if v equals 0, then we end up with this quantity being 0. Square root of 1 is 1. So E is mc squared. And since v is 0 in this condition, we call this the rest energy. So now we're going to refer to rest energy as E equals mc squared, which is the equation that the entire world knows when it refers to relativity. So here we have the relativistic energy and the rest energy, and also the relativistic momentum. One thing that comes about from the equation for rest energy, E equals mc squared, is the equivalence of mass and energy. So that is a really big concept where energy and mass are basically interchangeable. Any mass has some sort of energy stored in it. So you might hear the terms mass and energy being used interchangeably. Now, how about we figure out the relationship between relativistic momentum and relativistic energy? So starting out with the equation for momentum over here, we can divide both sides by v, and I'm going to skip the vector symbols. So we have p divided by v, then is m divided by square root 1 minus v squared over c squared. Now, if we multiply both sides by c squared, then the right side of the equation will look like energy. So I have p over v c squared is equal to the energy. So if we divide, if we flip this upside down really, and get v over c, then this will be equal to pc divided by e. So then E, which is equal to mc squared divided by square root 1 minus v squared over c squared. Now I can substitute the v over c, the v squared over c squared in here by pc over e. So that becomes mc squared divided by square root 1 minus p squared c squared over e squared. So I have this equal E, and if I square both sides, I end up with E squared is m squared c to the fourth divided by 1 minus p squared c squared over E squared. And if I solve the algebra here, I rearrange terms and solve for the energy, I end up with E squared equals p squared c squared plus m squared c to the fourth. So this is now the relationship between energy and momentum. And here we have this equation written out. Now, I mentioned earlier that the energy in the expression above, so this energy here, is actually the total energy. And the total energy is the rest energy plus the kinetic energy. So if we want to solve then for the kinetic energy, that's just going to be E minus E naught, where E is mc squared over square root 1 minus v squared over c squared minus the rest energy, which is just mc squared. So when we do the math, we end up with this expression for kinetic energy. One more little concept here, and that has to do with addition of relativistic addition of velocities. So remember from mechanics that when we dealt with different objects that are moving at the same time and we want to express velocities in terms of the different objects, we had subscripts and said that, for instance, this would be the velocity of object A with respect to object B, this would be velocity of object A with respect to object C, and this would be the velocity of object C with respect to object B. And back then, our equation just looked like this. VAB is VAC plus VCB, where we made sure that this subscript corresponded with that subscript. The B corresponded to the very last subscript, so we started out with A and ended up with B, and then this subscript basically dropped out from this entire quantity. So now to do the relativistic addition of velocities, we still keep the same order of subscripts. So we have VAB is VAC plus VCB, which is exactly the same thing that we had over here. But now we have to divide it by 1 plus VAC, so this order, times VCB, same order, divided by c squared. So the equation is similar but different because this time it has to do with the relativistic addition of velocities.